Hi everyone. Yeah, this is Dr. Venkateswarlu, Professor of EC, IARE Hyderabad. Yeah, today we are discussing about basic discrete signals. Here we are having that basic discrete signals, unit step function, unit impulse function, ramp sequence, parabolic sequence, signum function, exponential sequence, complex exponential, the rectangular sequence, triangular sequence, sinusoidal sequence, and sync function with the sampling function. This is the basic discrete signal. For implementing, manipulating the signals, the time we require the discrete signals like unit steps function, unit impulse function, parabolic sequence, signal function, yeah, including sampling function and so on. So due to this, we are entering that one by one unit step function. Here in this case, unit step function, so unit step function is denoted by u of t. That means where unit step function is followed by u of t. That using this all u of t, where it is followed by u of t. So within this u of t, it is defined. So here it is the what do you call 1? If it is 1, t. If it is t greater than or equal to 0 is the one limitation, and where if it is 0, t t less than 0. So using this all limitation, using this all condition, so using this all mathematical expression, we have to verify that this graphical representation of this. So where t versus u of t. Yeah, unit step function is followed by u of t. So we will try to define that u of t is equal to what you call t 1 if it is t greater than or equal to 0. So after that, if u of t is 0, t less than 0. Where within this graphical representation, based on this whole graphical representation, it is used as best test signal with the help of this unit step function. Of that area under this unit step function is unity, because of it is evidence is available where x-axis is the t versus u of t. That u of t with reference to that, so this area under this unit step function is unity. So like this, the unit step function is denoted by u of t. It is defined u of t is equal to 1 t greater than or equal to 0. 0, t less than 0. Now coming to this unit step sequence, the unit step sequence, it is followed by u of n is defined. So where u of n is equal to what you call 1 if small n greater than or equal to 0. So the time where so u of n is equal to 0, n less than 0. Yeah, in terms of this graphically, where n is substituted, where n is equal to what you call that n value, small n is equal to, so that elements are given where 0, 1, 2, 3, 4, 5, and so on up to what you call n value, where n minus 1 or n plus 1. Like this, if n is equal to where it is minus 1, minus 2, minus 3, minus 4, and so on. So with reference to this, the unit step sequence u of n is defined where u of n is equal to 1. If it is n what do you call greater than or equal to 0. Okay. So the time, so graphically you right to observe that one. Next, if it is u of n equal to 0, the time where n less than 0. Within this, so this particular n versus u of t. Yeah, similarly the shift unit step sequence u of n minus 1 is defined. So it is defined u of n minus 1. So if it is 1, what do you call n greater than equal to k. Okay, if it is 0, where n less than k, like this. So n versus where here also the substituted values where n is equal to where n is equal to, here also 0, 1, 2, 3 and so on up to what we call n should be in terms of that n greater than or equal to, where the greater than or equal to, okay, that k. If it is k is substitute, if it is that 0, u of n k is equal to 0, the time if it is what do you call n less than k. So within this, so graphically you write to verify that n versus u of n minus 1. That means it is the shifted unit step sequence u of n minus 1 is defined by using the mathematical expression graphically, that all sequence, okay, like this, we have to verify that all step sequences, okay, that positive direction and negative direction. Due to this, if it is here that where n is equal to minus 1, yeah, minus 2 or minus 3 and so on up to this, what do you call, n minus k, n in terms of that n less than k. So go on substituting these all values that are given elements, the shift unit step sequence u of n minus k is ready to define in mathematical formula and graphically. So we have to represent unit step sequence. Okay, this is required for what you call signal manipulation, signal strength, accuracy, accuracy information or signal. We will try to verify using this type of sequence. Next, unit impulse sequence. Unit simple sequence, or we can consider either it is unit sample or when the sequence it is defined. The sequence is followed by delta of n is defined as delta of n. So delta of n is equal to 1, whereas n is equal to 0. Okay. So here it is delta of n 0, where n not equal to 0. Within this, here we are to substitute that values are where here also say where n is equal to what do you call 0, 0, 1, 2, 3, 4 and so on. If it is the condition apply according to this unit impulse or unit sample sequence, the delta of n, so it is according to their definition, delta of n is equal to what do you call that one? Yeah, if it is 1, if it is right to substitute n is equal to 0. Okay, so here it is 0, where n not equal to 0. So that means go on substituting these all values. If n is equal to where n is equal to minus 1, minus 2, minus 3, minus 4 and so on up to where the n not equal to 0. So by using these all two conditions, condition 1 and condition 2, we need to define that in terms of the mathematical definition. So graphically, we need to verify that the unit impulse or unit sample sequence delta of n is defined in mathematically as well as what you call graphical representation for this definition. It is very much important for the sequence or given sequence or given signal, either it is unit impulse sequence or not. By using this all definition, we can try to manipulate the what you call that signals. So next, similarly, this shift unit sequence, it is followed by what you call delta of n minus 1 is defined, where the delta of n, so that the step unit step sequence delta of n, delta of n minus k, yeah, that n minus k is equal to, so if it is 1, so how it is varies. If it is 0, so based on this all limitations, so how it changes here. If it is this case n equal to k, first of all that n is equal to k, so how it is varies, where n not equal to, where n not equal to k. Within this, that the shift unit sequence delta of n minus k is followed by delta of n minus k is defined as delta of n minus k. Like this, the mathematical it is available. Here also go on substituting this n value, where n is equal to 0, 1, 2, 3, and so on. If it is n is equal to k. Okay. So like this, if it is n is equal to, where this case also, where n is equal to minus 1, minus 2, minus 3, minus 4, and so on. This case where n not equal to k. Like this, go on substituting this all elements, this particular sequence. Graphically, we try to verify this. Based on this, the shift unit step sequence delta of n minus k is defined, so mathematically as well as graphically. Yeah, next, the unit impulse function. Unit impulse function is denoted by delta of t, and it is defined as delta of t is equal to 1, t is equal to 0. So 0, t not equal to 0. Like this, graphically, graphically where t versus delta of t. Now try to verify that graphical representation. From this graphically, that mathematical expressions is involved here, where integral minus infinity to plus infinity. So the delta of in terms of that delta of t, where delta of t is, if it is 1, t is equal to 0. What happens that? Based on that case, where delta of 0, t less than 0. So based on this all notation, into dt. Okay. So using here, the dt is equal to u of t. Okay. So within this, if you want to calculate this delta of t, so now where delta of t is equal to, the derivative of u of t by dt. So the time we easily can verify that unit impulse function is followed by delta of t. So you can define in mathematically and graphically. So due to this, unit impulse function is how it is appeared in graphically and mathematical notation. Yeah, next, ramp sequence and ramp signal. Here, a discrete unit ramp function can be defined as. So here, where it is followed by r of n, where r of n is equal to n for n greater than equal to 0. Here, if it is r of n 0 for n less than 0, so you can define this a discrete unit ramp function. So r of n is like this. Go on substituting this n value. Here also same thing, where small n is equal to 0, 1, 2, 3, 4, 5, 6, and so on. That n less than, greater than or equal to 0. Okay, this is one aspect. The other, where n is equal to, here it is minus 1, minus 2, minus 3, minus 4, minus 5, and so on. The condition with reference this, where n less than 0. So with reference this all n value, so where r of n, that is a discrete unit ramp function, can be defined. It is noted as r of n. So when for n greater than, where n is, wherein that all n value for n greater than or equal to 0, what happens? And if it is n value is given, so based on if it is that 0, where for n, n less than 0. Okay, like this, write that all mathematical expression in terms of the graphically. So that you can decide that discrete unit ramp function will be defined using this all number of sequence. Okay. So ramp signal is denoted by R of t, and it is defined as like this, where t greater than or equal to t greater than or equal to 0, where 0 t less than 0. Like this here, t versus R of t. So now that signal will be appeared in terms of either like this, the signal. Okay. So the t value here also, here it is substituted the t value where t is equal to what do you call 1 or initially 0, 1, 2, 3, 4 and so on. So where if it is R of t, where R of t is equal to what you call initially that from origin 0, 0, 1, 2, 3, 4 and so on up to RF value, where t greater than or equal to 0, where t less than 0, using this all condition, where integral u of t is equal to integral 1, where that all t is equal to R of t. So if you want to this v of t, so using this all e of t is equal to derivative of dr of t by dt. So due to this, area under unit ramp is unity. Like this, you can interpret this both theoretically as well as mathematically in terms of that particular graphical representation, ramp sequence, as well as what you call ramp signal. Next, rectangular sequence. The rectangular sequence, it is denoted as rect of n with the length L is defined as what you call rect of n 1. If it is 1, n is equal to minus L minus 1 by 2 and so on, minus 1, 0, 1, 2 and so on, L minus by 2, 0, all the other n value. The rectangular sequence rect of n with length capital L is defined. Length is also assigned here, that L length value where it is in terms of this minus 1, 0, 1, 2, 3, 4 and so on up to that length, based on that length minus 1, where length is where L is equal to 8. Okay, that means L 8 minus 1, 8 minus 1, it is equal to what you call 7, like this by 2. Here also by 2, like this what you call rectangular sequence with length L is defined. If it is 1 comma where n is like this, and where 0, so all that if it is 0, all other n values. So here it is in graphically that n versus here that's n versus and rectangle what you call rect of n. So as you can analyze that one here, that n values here it is n values ready to observe by using the graphically 0 n is equal to 0, 1, 2, 3, 4, 5 and so on. What you call due to that length maybe L minus 1, L minus 1 by 2 in x-axis, this direction. Next, where n is equal to, where this side it is observed this all n by 2. Next, this side left side where it is where n is equal to what you call minus 1, minus 2, minus 3, minus 4, minus 5 and so on, L minus, it is the polarity, we know that how it is minus L minus 1 by 2 within this. So we can observe these rectangular sequences based on the sequence. So with the length L is defined in graphically that where n versus x-axis n, y-axis is what you call rectangular sequence. The rectangular sequence is followed by rect or UCT rect of n, that is followed by what you call, that all these parentheses, like it is either CTS or DTS, usually can recognize this. If you are using this where x of n, you know that x of n, where x of n with this particular parenthesis. Okay, like this, we try to verify this. The rectangular sequence rect of n with the length is L is defined with the mathematical formula with the graphical representation of this rectangular sequence. Yeah, next rectangular signal. Rectangular signal, let it be denoted as x of t. Maybe it is CTS, continuous time signal. Okay, and it is defined as x of t is a into rect of r by t. So this, if it is that a value is 4 or AC like here. So due to this all are back to verify it graphically. Where this r of t, x of t is a into r vector r by r. So the t versus x of t. Okay, t x-axis the t, and where x of t is y-axis. So within this, that x of t is, it is assigned, it is defined, it is denoted x of t, and it is defined as a into what you call rect of, okay, the rect of small r by capital T. So with the reference to this, so you can verify that graphically due to this a value is also assigned here. Right to observe here the t versus x of t. Yeah, this area may be what you call t by 2. Here it is minus t by 2 value. Okay, this is related to the rectangular signal for identifying. So the reference to graphically and mathematical expressions. Yeah, parabolic function. Parabolic function is a function of the form of f of what you call f of x is equal to x square plus bx plus c. Because you know that is the fundamental aspect of parabolic function, and if presented in the two-dimensional graphical form, it has the shape of the parabolic. Okay, the parabolic function is a function of the, it's a form where we know that f of x is equal to ax square plus bx plus c. Yeah, the equation represents the parabolic function is a quadratic equation with a second degree in x. Like this, we are to verify this all up. Okay, and x versus y, where y is equal to x square. If it is that x value is right to substitute here, you can verify this all are parabolic. The shape of this parabolic. Graphically, it is represented this parabolic function. Okay, the equation represents the parabolic function is a quadratic equation with a second degree in x. Okay. Yeah, parabolic sequence. A discrete parabolic sequence can be defined as, okay, it is followed by p of n is equal to n square by 2 for n greater than 0, 0 for what you call n less than what you call 0. Okay, and so on. We have to define the discrete parabolic sequence can be defined in terms of the p of n, where here also t versus, okay, that p of n value, like this. We have to verify that okay, n is equal to where n is equal to 1, 2, 3 and so on, 0, 1, 2, 3, 4 and so on, and it is where n is equal to minus 1, minus 2, minus 3 and so on. Now coming to our discrete signum function. A discrete signum function can be defined as, so it is represented the signum, discrete signum is followed by SCN, signum of n if it is 1, so 1 n greater than 0, 0 n is equal to 0, minus 1 less than 0. Okay, with this n versus signum of n. So like this, you have to represent this all functions, discrete signum function where n versus what you call signum of n. Okay, signum function is defined as signum of t. It is defined as the signum of t is using the same condition where t, the element t, 1 t greater than 0, 0 here t equal to 0 minus 1 t less than 0. So here within this the signum of t versus Texas where signum of t is equal to, so 2 ut of minus 1. So like this it is represented signum of t, and from this origin minus 1 here, signum of t is equal to 2 into u of t minus 1. Okay. Now coming to the exponential signal. Exponential signal is in the form of x of t is equal to e power what you call alpha into t. The shape of the exponential can be defined by alpha. So how we are representing this all are because of we are having a lot of notations are condition based, like case 1 it is mentioned the case 1 if alpha equal to 0, it is mentioned the case 1 where alpha is equal to 0, that exponential signal, the exponential signal is in the form of x of t, where x of t is equal to e power 0. Because of alpha is it is assigned 0, where e power 0 equal to that 1. Like this. So this is the case 1. Based on this case 1, the t versus, based on the t versus x of t, where x of t is nothing but the exponential signal in the form of what do you call e power alpha t. So that value is substituted where alpha equal to 0. So it is right to verify that case 1 variations. How it is appeared that t versus x of t. Yeah, next here coming to the case 2 where that alpha less than 0. That is followed by what do you call negative. It is represented that negative. Then that exponential signal x of t is equal to e power minus alpha t. The shape is called decaying exponential. This is all in terms of the t versus x of t. Now it is decaying. Now it is called decaying the exponential. Decaying exponential. What do you call shape like this? Okay. This is in terms of the second condition. Case 2. Next, coming to the third case, case 3. If alpha greater than 0, that is positive. This polarity is indicated. Here it is negative. Now it's coming to the positive. Then x of t is equal to e power alpha t. The shape is called rising. What do you call rising exponential? Here it is decaying exponential. Here is rising exponential. Okay. So this type of exponential signals are required for what you call signal manipulation and signal strength verifying analysis t versus x of t. Okay. Next, come to the exponential composition signals. Here we know that everybody knows that's one. The complex exponential signal sequence is a form of where x of n is equal to e power j omega naught n. Again, it's by this also involved with Euler's formula where x of n can be expressed as so like this, where x of n is equal to what do you call e power j omega naught n into cos omega naught n into j sine omega naught n. That means this x of n is a complex sequence whose real part is cos omega naught n and imaginary part is sine and omega naught n. Okay, this is related to complex exponential sequences with what do you call sequence in the form of x of n, where it is either CTS or TTS. It is decided in the factors. It's the same thing if you are applying the what do you call DTS, discrete time signal, by interlinked this particular using that Euler's formula, that x of n can be expressed. This x of n is equal to where it is complex sequence whose real part is this one or imaginary part is sine omega naught n. Now the real exponential sequences, so using the different cases or notation here, if it is, we have to consider the real exponential sequence x of n is equal to c into a power n. Okay, like this. If c and a in the this above equation, like x of n is equal to c into a power n, are both real, then x of n is real exponential sequence. Followed? Okay. Four distinct cases can be defined. Like the cases may be a, what do you call, a greater than 1, where a less than minus 1, where minus 1 less than a less than 0. So what happens? This real exponential sequences, it is given x of n, where it is given that where x of n is equal to c into a power n. So using this all four conditions, 0 less than a less than 1, so how it is varies, what do you call it, graphically. So within this, so if it is a greater than 1, 0 less than a less than 1, minus 1 less than a less than 0, and a less than minus 1. So now it is right to represent this all sequences, exponential sequences, where n versus how it is the varies that are. Okay, condition, if it is a what do you call, a greater than 1, so that sequence will be the real exponential sequence is like this. Okay, real exponential sequence. The condition 0 less than a less than 1, so what do you call this, the shape is like the sequence is following like this. Okay, inverse. Okay, next if it is minus 1 less than a less than 0, so here it is n versus how it is appeared that what do you call that n value and so on. Okay, next coming to this sinusoidal function. The sinusoidal sequence can be expressed. Everybody knows that from the sinusoidal sequence, how they are expressing, either in mathematically or graphically. Yeah, there is a possibility in sinusoidal waveform or sinusoidal what do you call graph. But here we should recognize that all sinusoidal sequence can be expressed as what do you call x of n is equal to a into sine of omega n plus pi. Okay, here the sinusoidal function is like this. According to x of n is equal to a into sine of omega n plus pi. Okay, so sinusoidal signal is in the form of x of t. Okay, here it is x of n. Here in terms of the x of t is equal to a cos of omega naught plus or minus pi, or we can write a into what you call a into sine of omega naught plus or minus pi. So when compared to this x of n, where x of n versus what we call x of t. Okay, so similarly we are right to verify that our case where x of n, with this we can change this all parentheses, the meaning is very different. Okay, you can consider this are all nothing but what you call continuous time signal. Okay, these are all our discrete time signal. Okay, like this t versus x of n. So that t naught is ready to verify 2 pi omega naught. Okay, yeah. Now discrete signum function. So the discrete signum function can be defined as x of n is equal to a into 1 minus mod n by capital N. Okay, it is represented graphically n versus x of n. So here n here it is n is equal to what you call, here n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3, 4, 5, 6 and so on. Here also n is equal to minus 1, minus 2, minus 3, minus 4 and so on. Here according to this condition, x of n is equal to a into 1 minus mod n by capital N. This you can represent in graphically. The triangular signal, so let it be denoted as x of t, where x of t is equal to a into 1 minus mod t by small t by capital T. Okay, it's also we have seen the signal function also it is try to define mathematically. Here in physics and engineering, the signal sinc function denoted by sinc of x. In mathematics, historical unnormalized sinc function is defined for n not equal to 0, and so on. So on. You can apply the different what you call subject or maybe a stream and so on. In our case, the discrete sinc function can be defined as sinc of n is equal to sine of pi n by pi n. Like this, right? To represent value at plus infinity is to 0, at 0 is to 1. So value t minus infinity is to 0, maximum is 0. Okay, like this, the sinc function, it is denoted as sinc of t, and it is defined as what do you call sinc of t, where t is sinc sine pi t by pi t, where if it is one substitute 0 for t is equal to plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and so on. This you can represent in graphically, where t versus and sinc what you call t. Okay, these you can represent mini graphically. Okay, next coming to this, somewhat is elementary signals are involved here. Under elementary signals, it is followed by what do you call variation between. Okay, how the signals are involved with the elementary signal. So here the elementary signals are used for analysis of system. So now that signals, just now we have verified the all number of what you call signal versus a system. The time it is a major role in elementary signal. The elementary signals are used for analysis of systems such as signals are step, impulse, ramp, exponential. The time we refer to step signal, what you call impulse, ramp, exponential, and sinusoidal with this involved with the elementary signal. The elementary signals are used for analysis of system. Okay, that's why this is the most important in elementary signal for deciding the system related parameter. Okay, elementary signals, whenever we try to attach numerical quantities to phenomena, numerical quantities are another numerical quantities. Okay, so using this all numerical quantity like what you call that elements, maybe terms of signal, maybe samples and so on. Attach the numerical quantities to a phenomena, we need a reference frame. Okay, so this starts from the moment we learn how to count. So when our fingers become our own reference frame, isn't it? Either 5 or 10 or whatever you say, the left what do you call left finger, left side or right side or whatever it is. Okay, so to the time we learn how to write the number when the powers of 10 becomes the reference frame. Okay, the worst which can happen to a person so is to find him or herself into what you call a situation where there is no reference frame. Reference frame is available. Reference frame is available that you can decide the thing. Now, right, to find that him or herself into a situation where there is no reference frame. How it is so okay, analyze. So in the middle of this discrete or of the vision without any instrument, or maybe what you call among the people speaking a totally foreign languages, and so on. So using the solar, which can happen to the persons to find him or himself. Okay. In other words, without a reference frame, we are lost. What things are lost? We can decide the thing like this. So there is involvement with this elementary signals. So, but the time we learn how to write the numbers and the powers of the 10 like this, we can consider a lot of example, real-time examples can decide the factor. Okay. In signal processing, we have the same problem. We need a appropriate reference frame so that we can place the signals. We try to analyze. Signal is if the frame wise, the signal is without frame wise. So based on this, the signal processing, so an appropriate reference frame that we can place the signal, try to analyze and estimate the desirability. So since we deal with this signal, any reference frame of interest has to be made of signals with well-known properties. Without these all properties, we cannot analyze. We should reflect this kind of information we want to extract. Okay. So, for example, if we hear the musical note and we want to determine which note it is in the scale, or maybe we need to compare it with the sinusoidal signal, or maybe sometimes the tune, or maybe tones, maybe some waves, whether it is dot wave file or different file, at all frequencies, and determine which frequency is the closest, which one is the closest, what you call the signal, maybe tone, or what do you call that, peak, spikes, the peak to peak, or like this. Okay. In what follows, we present some of the elementary discrete time signal. Okay. So which will be at the basis of the analysis developed in the rest of DTS, discrete time systems, and maybe what do you call, so on with reference to DTS, discrete time signal, discrete time systems. We have to estimate the element based on these elementary signals. Yeah, now come to the discrete time unit impulse. Here it is discrete time unit impulse is it is denoted by what you call delta of n, is the most elementary signal, and it provides the simplest expansion. It is defined as delta of n, where here the delta of n is equal to 1 if n is equal to 0. Delta of n equal to 0 otherwise. Okay, and it is plotted. Yeah, using this all definition, you can plot this graphically together with the general shift version delta of n minus k. How it is shifted here. So an impulse of n and shifted nk. Here it is impulse of n versus delta of n. How it is shifted as per this delta of n minus k. So now it is shifted from here to here. Okay. Now that shifted impulse n comma k, like this, that time we recall the discrete time unit impulse. Okay, that unit impulse most elementary signal, and what do you call it provides the simplest expansion based on the delta of n is equal to 1. If small n is equal to 0, we are delta of n 0. Otherwise, how it is varies, we can estimate that what do you call either impulse of n x n or shifted impulse n k. Like this, we'll try to interpret. Okay, any discrete time signal can expand it into the what you call superposition of the elementary shift impulse in terms of this maybe in impulses. Each one represent each of the samples, this expression as x of n, that is what you call DTS, discrete time signal. X of n is equal to the summation k equal to minus infinity to plus infinity x of k delta of n minus k. Okay, that means you can decide that where x of n, that x of n may be what do you call that x here, that x of where x of n is the DTS, but this x of k either may be what do you call, using this discrete time impulse response variation. How it is the varies that k value is minus infinity to plus infinity. Let's go on substituting this all value where k value is k is equal to minus infinity to plus infinity. Okay, and delta of n minus k, where each term with x of k and delta of n minus k in the summation expresses the nth sample of the sequence. Like this, we can decide that where n is equal to minus what you call n versus x of n. Okay, the 10 value minus 0.5, so 1.2, 0.5 or 1.6 and so on. So where n is equal to minus 1.0, 1.5 and so on. You can analyze that all discrete time unit impulse is expanded. So what you call that element shifted impulses. Each one is represented each of the samples due to this particular expression. Okay, this is the best example like sequence. Here using the same sequence. Okay, so with reference to this, we can decide the what you call how it is expanded, where x of n values like this. Okay, and like this discrete time unit impulse is so it will varies that the significance of this expression in the fact that any signal, no matter how complicated, is decomposed into elementary pulses. Is it properly or not? If it's properly scaled in the amplitude and shift in time of particular interest in the unit step sequence, u of n is equal to like this. U of n is equal to 1 if n is greater than or equal to 0, 0 otherwise. Okay, if yeah, it is the simple exercise to show that what do you call u of n is equal to the summation k equal to minus infinity to what do you call that n small n delta of k. Like this unit step sequence will be appeared where n versus u of n. Okay. Now coming to the CTUI, that is continuous time unit impulse. Here the discrete function, the continuous time, we have to be a bit more carefully. A unit impulse delta of t is defined as a function which is 0 for all t not equal to 0, and at its integral is non-zero. Otherwise, if it is the continuous time, so if it is unit impulse delta of n is a function which is 0 for all what do you call in particularly delta of t is such that what do you call delta of t is equal to 0 for all t not equal to 0. So that integral minus infinity plus delta of t into dt integral, so 0 minus delta of t dt equal to 1 like this, and it is represented as direct delta function. The direct delta function is like this, that you can decide that it can be viewed as the limit of the sequence of the rectangular signal of width t with the height 1 by t as t tends to 0. Okay, it is significant in the fact that for any signal x of t continuous at the t, we can write this particular expression, mathematical notation for this. X of t will be appear integral minus infinity to plus infinity x of t minus tau into delta tau into d tau integral 0 x of t minus tau delta of t d tau. This is known as the particular shifting property. Okay. So here using this all, after applying this shifting property, how it is changed the x of t. Easily we can calculate the x of t at the continuous time unit impulse function. So if you are not having this shifting property, here that shifting property, so we are unable to estimate the continuous time unit impulse function. So rightmost integral in the previous expressions is easily derived by the changing in the integration variable. What purpose? Comparing to the equivalent expression in discrete time, either in terms of here it is involved that based on this continuous time signal, after that we can decide this discrete time signal. Okay, you can see that in both cases we expand the signal continuous time or discrete time in terms of sequence of unit symbols. Of particular interest is the unit step signal is defined is u of t, where u of t is equal to, so what do you call, so 1 if t greater than or equal to 0, 0 otherwise. It shows that is the simple exercise to show that for representing the u of t, it is unit step signal is defined based on the definition. We will usually can represent in graphically. Okay, that graphical representation for this, like this, we can ready to observe here t versus u of t, like here. So easily can represent this solar where t, the t versus what you call that u of t, So within this, if it is u of t is equal to integral minus infinity plus delta of tau into d tau. So within this, I have to verify here. Okay. Now it is like this. Okay. Here it is one. Okay, unit step signal. Unit step signal will be appeared. So like this, a discrete time signal is defined at discrete times, like n versus x of n. We know that where x of n is equal to a into a power n, that n value is substituted here. That means here that continuous time signal, it is followed by x of n. You know that one is equal to a into a power n, where that n value, is ready to substitute where n is equal to 0, 1, 2, 3, 4, and so on. Go on, substitute with n value. So what happens? We have to verify that discrete time signal is ready to observe that at discrete times. That is n versus x of n. Like this, right, to n versus x of n. So I have to observe this type of what you call discrete time signal. Okay, this is all elementary signal already we have seen. Sinusoidal exponential, everybody know that one. This that signal classification is involved from this for estimating the elementary signal. Signals are classified into two categories. We know that one just now we have discussed. Like in what you call here, it is nothing but a continuous time signal, and with the discrete time signal. This is one aspect. All are involved with this. Here also we require that what you call elementary signal. Here also how it is varies with effect with this elementary signals. The signals are classified in the following the categories. All categories also it is depending upon either continuous time signal or discrete time signal. If it is deterministic or non-deterministic signal. Okay. Is after that even and odd signal we try to estimate. Of course, periodic and aperiodic signal already we have seen that on starting itself. But here it is there is a deciding factor with either it is how it is varies the CTS and the TTS, discrete time signal, continuous time signal. After that, the energy and the power signals. Okay, after that we can decide that real and imaginary signals. Okay, now the continuous time, discrete time signal. So within this, the signal is said to be continuous when it is defined for all instants of the time. Here, this is the fundamental aspect: time versus amplitude. Okay, so after that, the what do you call? So a signal is said to be discrete when it is defined at only discrete instant of the time. So that means signal is said to be continuous when it is defined at all instant of the time. The continuous, okay. If it is discrete, so only discrete instant of the time. So the continuous, it is represented here, and discrete, same, we can consider this all discrete time and amplitude and so on. Okay. The signal is said to be a continuous time when it is defined for all instant of the time. This represents a graphical representation of previous, and now they can define that continuous time. The signal is said to be a continuous time when it is defined for all instants of time. The real-time examples of the continuous time signals are telephone signal. Always it is involved with the CTS, continuous time signal. So real-time best example is telephone signal. Okay. The telephone signal, how they are estimating with this continuous time and maybe discrete time signal. Yeah. A signal is said to be a continuous time when it is defined for all instant of time. The real-time examples of the continuous time signal are telephone signal, or video camera output and temperature variations and so on. So many parameters are involved in CTS, continuous time signal based, like this. Okay, a signal is said to be a discrete time when it is defined at only discrete instant of time. How it is identified the discrete time? Yes, a real-time example of the discrete time signals are quarterly, vertical gross national product, or monthly sales of the store, stock market, daily, or what you call weekly or monthly, and so on. All numerical or graphical estimation of with a signal is said to be discrete time when it is defined at only discrete instant of the time. Like this, we have to verify that real-time aspect of this continuous discrete time when it is real-time example of the discrete time signals are okay, like this graphical representation. Yeah, deterministic and non-deterministic signal. Okay, a signal is said to be deterministic. So we are talking about that signal based. We are listening my goods. How we are listening my goods, either .wave file or what you call voice signal, or maybe analog signal, or whatever it is, analog signal. The signal is said to be deterministic if there is no uncertainty with respect to its value at any instant of the time. All signals which can be defined exactly by a mathematical formula are known as deterministic signal. Okay, the thing it is assigned, the signal is said to be non-deterministic. If there is uncertainty with respect to the value at some instant of time, non-deterministic signal are random, okay, in nature, hence they are called random signals. Random signals cannot be described by a mathematical equation. They are modeled in a probabilistic terms. Okay, so we can analyze this all based on this all too. The definition or interpretation of the deterministic, non-deterministic graphically, with noise or without noise, usually can identify that which one is the deterministic or non-deterministic signal. Okay. With this, a signal is said to be deterministic if there is no uncertainty with respect to its value at any instant of time, or signals which can be defined exactly by a mathematical formula are known as deterministic signal. So it is represented graphically. It is time versus x of t. That is time versus what you call CTS, continuous time signal. Okay. So like this, signal is said to be non-deterministic if there are uncertainties here. When compared to this and this, uncertainty with respect to its value at some instant of the time. Okay, non-deterministic signal are random in nature, hence they are called as random signal. Random signals cannot be described by a mathematical equation. They are modeled in probabilistic terms. Okay. So like this, we can deciding these all factors. Okay. Okay, we'll continue next.
Like, share and subscribe. Hit the bell icon for more updates.